and who care about this crossroads of environment and cryptography, and it's going to be a really interesting topic. We talked with Alan for a couple of minutes before, and it seems that he's really into it. So let's welcome Alan to the floor and see what he has to say about it.
Awesome. Thanks so much. Awesome. Hi, I'm Alan. I started a project called Filecoin Green, which is part of Protocol Labs and focuses on connecting the Filecoin network to renewable energy. But my talk today is going to be a little bit more broad, really talking about environmental claims in general. So renewable energy, you're saying that this node in a network uses 100% renewable energy. That's one type of environmental claim. But what I'm going to be talking about is the fact that we need better tools for justifying environmental claims broadly, and talk about how data provenance is a really good fit for a lot of the tools that we're building in Web3. So I'm going to first build out that thesis, right? So why do we need new tools for impact evaluation and environmental claims? Then talk about something that we've been building called transform.storage. If you go to transform.storage right now, it'll redirect to CO2.storage, which is the prototype that we've been building specifically for carbon offsets. But I'm going to be talking about these tools sort of broadly and what they can be used for in the near future. I'm going to talk about what's built right now. So how can you use this to prove impact in projects that you're building right now today? And then give you an opportunity to actually use some of these tools to decarbonize your travel here for free. So if you have a Brave browser with a wallet set up, or if you have MetaMask on your phone, you can scan a QR code and say how far you traveled and automatically retire carbon offsets and build automatically on your phone using decentralized compute and anchored in content address data types, build a carbon ledger for your travel here and offset that with credits from the regen network. And so firstly, why do we need new tools for impact evaluation? Well, so all of these claims that we make, all of these environmental claims, they're claims about the real world, right? And so here's at the top some examples of carbon offset projects and renewable energy certificates, right? So these are used to make claims about net zero companies, net zero projects, net zero activities, or claim that we're using renewable energy for a particular purpose. And they're used to make statements like this, right? So my trip to ETHCC was net zero, or our power bill last month was 85 kilowatt hours, or our regenerative farm removed a certain amount of carbon, or we recycled so much e-waste, right? These are claims about the real world, and we need better tools to justify them than the ones that we have. So RWCs are not like ownership, right? They're not like, you can't just verify that you own an RWC and verify that you own an NFT and therefore automatically trust that the data there is accurate, right? If you're trying to say, okay, my power bill last month was 85 kilowatt hours, you can't just go to a chain and say, if you want to verify that, you can't just use just on-chain data to do that. They're not like price, right? The information isn't distributed, so having 100 different people vote on what my power bill was last month doesn't make a lot of sense, right? Because 100 different people don't have access to that data. I have access to that data, and my power company has access. It's not like state. We need a lot of compute to determine many of these real world claims. So we were just talking about satellite data before. If you try to do, if you try to compute over a satellite image on chain, you're gonna run out of money to pay gas fees really, really quickly, right? So we need compute over data. It's not like identity. Identity is a useful building block, but just establishing someone's identity through a DID or a VC or a wallet address, that doesn't give you any sort of assurance that what they're saying is actually true about the real world, that what they're saying about my power bill matches the facts on the ground about my power bill. It's not like a market. The fact that someone is willing to pay a lot for a data set doesn't actually mean that that data is true, right? Often it's the reverse, right? If I can establish that this data is true, someone will be willing to pay for it. But you can't just use a market to solve that problem automatically. It's not decentralized physical infrastructure. We don't want to come up with new ways of building new consensus mechanisms every time we want to validate something new, right? We need something that is faster and more plug and play. And it's not uniform, right? So different data is validated differently. If I am claiming that my project or my company is net zero, there's going to be a ton of different data sets that go into that claim, and they're going to be validated using different methods. So how do we get the benefits that we talk about in Web3 about verifiability while respecting the nature of real-world claims? So here's the big bait and switch of this talk is you come for the sustainability and stay for the category theory. So we're modeling these sorts of claims as compute graphs. And so the idea here is that you have a compute graph where data comes in one side from the left and leaves to the right. And a line in any of these compute graphs is a data set. That data set is typed, and the type itself is content addressed. So we'll talk a little bit more about that and why we're setting things up that way. So a line is data, and a box is a function or a transformation that happens to that data. That function might be entirely public and verifiable because it's public. It might be part of a zero knowledge proof. It might happen entirely offline, and you just know that you can trust it if it was done by someone you trust, right? There's a bunch of different trust models that can be built into these functions, but the idea is a line is data, a box is a function or a transformation to that data. And then functions can have multiple inputs or multiple outputs, right? Functions can also compose. So if the output type of one function equals the input type of another function, then you can plug the first function into the second function, right? And so this is all based on this paper here, wiring diagrams as normal forms for computing in symmetric monodal categories, which we could talk about. I think there's going to be some questions or some time for questions afterwards if you have more thoughts about sort of where this comes from. And so I said that all this data is based on content addressed data and content addressed types, right? So why do that? Why is that important for real world claims? Well, like I was saying, different types of real world claims are going to be justified using different methods, right? And if you anchor your data in content addressed data types, that gives you portability and interoperability between different data stores and different sources of compute over your data. So you can store your data a bunch of different places, and as long as you know that the data itself is content addressed, you can verify that the data is the same across all these different data stores. And if you use content addressed types, then you know that data of one type, which can be verified across all these different data stores, is going to plug into compute of a type that exists on another data store, but you can verify that the types are the same, right? So this is just using content addressing to verify across all these different platforms. And so, the structure of a real world claim, right? So I talked about connecting Filecoin to renewable energy. That's what we focus on. So you may have different types of data that verify different types of this process. So on the left here, you have the certificate that comes from a Filecoin node proving their actual energy use using their power bill to a third party. That data is signed. You can use that data in an ERC-721 token. You can get, if you go to greenscores.xyz right now, you can see a bunch of these outputs from different storage providers who have gone through this process. So this is validated data based on a power bill. We also have information from the Filecoin chain that we can use to estimate the amount of energy use by a storage provider over a given period of time. Right, and so these give you different types of information. So what would this look like in this RWC compute diagram that I was talking about? Well, so you have data coming in from these different sources, right? You have data from the Filecoin chain, you have data from this energy validation process. Again, lines are data, boxes are functions, and data travels from left to right. And so you then plug that data from the chain into this function that gives you these estimates, right? So that's one transformation that you're doing to that data. Again, all the data is content addressed, all the types are content addressed, and in this case, the function is public, and you can just rerun it, and that's how you get your verifiability. Then you put both of those different sources of information, so the energy estimation that's based on on-chain compute, and also this validated information from the power bill into this green score calculator, which again is public. It gives you this green score that comes out. So this is an example of how we can track different forms of justification for real-world claims that interoperate between different platforms and different sources of information, right? And so how does this plug into what we're calling transform.storage and the prototype I mentioned, which is CO2.storage, where we're experimenting with a lot of these concepts? Well, so real-world claims don't just have a single layer of compute information. They actually have 3 layers, right? So at the base layer, you have data assets. So this is the raw data that is transformed by all these different functions, and ultimately what your claims are based on. On top of that, you have functions, right? So at the function layer, an input is a type, and an output is a type, and the boxes themselves are the definitions of functions. Then on top of that, you have provenance, right? You want to know, where is my verifiability coming from for all of this different data and all these different functions and all of the compute over data that we're doing. So you can take individual pieces of data, you can sign them with this provenance information and establish, do I trust the source of this data, or do I trust the method of verifying data? Say something is really good for like a decentralized Oracle, right? The provenance information just says, okay, that's where I got this information. I got it from Chainlink or somewhere. Or it says, this data was validated by this particular auditor who knows a lot about validating this type of information for this purpose, right? So that's what the provenance layer is for. Or it says, who wrote this function, right? Do I trust this person to have enough domain expertise in that area in order to write a good function for this type of data transformation for this real-world claim? So that's the provenance layer, right? So we have compute diagrams over these 3 different layers, right? So the raw data, transformations to that data, and then provenance of both those functions and that data itself. So what's the actual sort of like type structure of this? What's the data model look like? So you have this very simple compute diagram where just one data set comes in, it gets transformed by a single function, and then the output data comes out, right? And that exists at these 3 different layers. So we'll start with the function. It's pretty simple. You have a function. This function has an input, which is a type, an output, which is another type, and a definition, which is just sort of raw data, right? Then that type has a schema, right? So you want some way to know, based on a content address type, that your data conforms to that type, because then you know whether you can plug it into this function, and you also know whether your functions can compose, right? So that's the next kind of key to all of this. On top of that, if you want to actually flow raw data through this compute pipeline, you have data assets. And a data asset says, I have some data, it conforms to this type. Then on top of that, you have provenance information for the raw data and the functions themselves. And you wrap all of this up into a pipeline. Every individual piece of data here has its own CID, and your pipeline itself has a CID, right? And so that pipeline says, here is all of the data I'm using, here's how that data is transformed, here is who provided that data or the method that I'm using for verifying that data, here is who wrote all of these functions, and then the provenance information of that CID says, I carried out this computation, and I say that when you take this data and input it into this compute pipeline, this is the data that you get out, right? So you're able to trace provenance at all of these different hierarchical levels of these data structures. And so, an example of this, using this for a claim would be, you could take a hypercert, which is from the network goods team at Protocol Labs, and the Hypercerts Foundation, I think in collaboration with Supermodular. And you can say, okay, this hypercert tracks impact or actions that have impact. You can then use a property of that hypercert to point to a pipeline or the provenance associated with the pipeline and say, here is how I reached that conclusion about the impact that is tracked with this hypercert, right? And maintain that both the hierarchical provenance information and the traceability of that claim across all of these different platforms where you might want to actually store and compute over data. So if you're interested in more about how we're thinking about this, this paper is a work in progress, but this is sort of where a lot of this stuff is going, is this data provenance over computational graphs paper. Also at the upper left or upper right hand corner, if you want these slides, you can scan that and get them. So how do I actually use this to evaluate impact in my project? Like what's built right now that you could use if you want to start using this like today? So the checkboxes here are stuff that we've implemented, documented, and have a UI at for CO2.storage. Has a API too. If you actually want to like use this at scale. So you can write out schemas, associate those with content address data types. You can make assets. You can easily allow your users to create assets based on this entire model, and you can tag all of that with provenance information. This stuff is partially implemented. There actually is like a UI for a lot of this now, and it's coming pretty soon. But we're going to give you a chance also to create a data pipeline in order to build automatically using decentralized compute over data. So Project Bacalhau give you the ability to make a carbon ledger in just a couple minutes that is going to certify that your travel here was net zero. So, I said you can type in a data schema. This is what the UI for that looks like. You could do this by hand if you want and just type in, say, there's all these different field types. You can say, my record is going to have this set of different field types, and do that in the UI if you want. You could also just use the API to import a JSON schema that already exists. Then, again, this gives you a type that is anchored in a content address, right? So that means that that type is portable across different compute environments. And so that's like really the secret sauce to this whole thing, right? Is you need not just data that is verifiable across different environments, but data types that are available across different compute environments where you want to do that compute. Because the methods that you're going to use to verify different types of data are inherently going to be different based on what you're verifying and what your real-world claim actually is. Right, so you can use this UI, you can type out your schema, you can use the JS API, you can import your own JSON schemas if you want. Then you can take the CID of that type, and right now you can just enter that into form.co2.storage/that CID, and if someone opens that in Brave with their wallet set up, or if they open that in the MetaMask browser, they just have a form that looks like a Google form, except you log in with your wallet, you enter that information into the form, and you sign it with your wallet address, right? So that's how you get the provenance information associated with an instance of a data type, right? So that makes it really easy to just collect information from, say you have a carbon offset project, say you're working with a ton of people on the ground who need some easy way of giving you information that is tagged with those provenance data sets. Then you can just send them that link, right, and have them fill in that form. They don't need to know that much beyond having their wallet set up. And so this is the data model for that. Then, like I said, their data contains auditable provenance information that you can just verify in the browser. So you can just take their signature over that whole data type, including the schema itself, and verify that they actually contributed that data. And then you can use that. Say you have data from 20 different sources. It's all signed with provenance information. If you know who contributed it, then you know whether or not you trust all of the inputs to a compute pipeline that gives you your real world claim, right? So this is the situation in a lot of, say, net zero claims or claims about issuing carbon offsets, right? Your data may come from 20 different people on the ground, and also the validation and verification body, and also the carbon offset registry, right? And then ultimately you're matching that to some estimate of your emissions that comes from a different source. You might have data from 10, 20, 30, hundreds of different sources. If you can track the provenance of all of that information automatically, and then show how that flows through a compute pipeline, where the steps of that compute pipeline are done in different compute environments, that's what we need in order to actually verify real-world claims. So, what's coming next? Data pipelines actually have been implemented. They weren't when I initially made this slide. Private data, encrypted data, there's a bunch of different ways of doing that. Monetizing your data and code, and things like impact evaluation as a service. So giving people the ability to certify different types of impact and maintain these provenance pipelines, which can then be extended when people want to add to them, or use that impact to match against something. So decarbonize your travel for free. So if you have Brave with a wallet set up, or if you have MetaMask and you want to use that to sign a record, what you can do here is scan the corresponding code here. You can enter in your name and how far you traveled and what the event is and what the date is. And then it'll take a couple of minutes because this is actually using Project Bacalhau. This is using decentralized compute over data. But we will calculate the amount of emissions associated with your travel. We'll then automatically retire an offset on the regen network. That money goes to one of several different carbon offset projects that are avoiding or sequestering or removing carbon through ecosystem benefits. will then create a record that gives you the hash, the transaction hash of that offset, matches that to your actual travel, and then gives you a carbon ledger, right? That is expressed as this simple data pipeline, right? So one record goes in, it's this function transforms it, and then the record that comes out certifies that your travel was canceled out by that carbon offset record. Happy to take any questions, and also to answer any questions about the demo if you're trying it. Thanks.
If you have any question.
Hi there, thanks for that, fascinating. Just wondering where you are on getting traction with this. Like 3 months ago, I tuned into EY doing a conference about their blockchain solutions that they're developing on Ethereum, and one of the things they were demoing were carbon tracking capabilities through a supply chain. I'm just wondering how much engagement or discussions you're doing with like business parties who really care about this sort of stuff at a sort of like business and enterprise level, not just at the personal level. Thanks.
Yeah, totally. Yeah, we know the folks at EY, and we've talked to a bunch of different people in this space. So yeah, we're pretty actively pursuing that. There are a few different refi projects that are actively building on top of this too. So looking to both go after all the sort of Web3 native stuff, and then sort of expand into a lot of the more traditional corporate areas where people really, like you're saying, really care about traceability and carbon offsets, right? And I think especially what we're seeing is that over the past 6 months or so, that's really come to a head as there have been sort of a lot of revelations about some of these carbon offset projects, right? Which have shown that some of the carbon offsets, many of the carbon offsets that have been certified by some of the largest registries, like were not actually very good. And so, they're really actively looking for ways to establish the provenance underlying the claims that they're making, right? We work really closely with, an example of that is this project called Gainforest, which takes actual satellite images that are updated every 2 weeks, plugs them into a data processing pipeline, and shows that either this carbon offset is really good, it's really protecting a forest in an area that is at risk of deforestation, or showing that, okay, this registry made this claim, but it actually is not backed up by data because there is, say, deforestation in that region. So yeah, pretty actively going after that.
Awesome, thank you.
Hi, thanks for the presentation. I think absolutely brilliant. Just thinking about it from implementation perspective. So some of the challenges that we've been having currently, we're using satellite data, and our challenges are more around scalability and performance. So how does this scale up from performance perspective, responses, and scalability? So basically, that's the question.
Yeah, I mean, so we're building this on Filecoin and IPFS, right? And so Filecoin has huge scale, right? It's something like 13 exabytes of data storage capacity. So you can take like all of the data across all Web3 projects and store them thousands of times just with the data storage capacity that Filecoin already has. It's something like it's between 5 and 10% the total size of AWS. So from a data storage capacity, we're pretty good. I think that from the compute over data perspective, right, like there's a bunch of different answers to that, and it's evolving pretty quickly, right? I put 10 different logos of places that you might do COD. And so we're using Project Bacalhau, which is a project that takes all these different nodes and compute capacity that is underutilized in mainly Filecoin, and allows people to use their CPUs and GPUs to contribute to this decentralized data processing network. But the whole point, right, that I emphasized a couple times is like you could plug this into a bunch of different COD solutions.
So just a quick follow-up question on that. So based on a normal implementation that you've spoken about right now, what have you seen in form of latency and those challenges, in being able to scale up? So we're looking at something around 15 to 10 minutes on an average for a data set to be computed and stored. So does it play nice with this requirement at all?
Yeah, I mean, so it depends a lot on what exactly you're trying to do, right, and what the design requirements are. One of the things that's useful about an architecture like this is that you could easily get the computational graph, which is like rigorously and verifiably tied to the actual data that you're working with. And that graph is pretty small compared to those data sets. So something you could do is like, have this potentially very large compute pipeline and know what the CID is and what the size of each of these data sets is that's coming in. And then you can just like inspect the pieces that you actually care about for a given job, right? But the details on like what exactly the compute time is and latency and stuff, like that would have a lot to do with the specifics of what you're trying to do.
Thank you. Last question.
Really cool, thanks so much. I just tried it, worked like a charm, so that's really cool. I just wondered if you could talk quickly about the integration with regen and how that works, and specifically how that relates to the provenance layer in the diagram.
Yeah, I mean, so right now, if you inspect the compute pipeline that came out of what you did, right, there's a transaction hash there, and so you can enter that into MintScan, and it should have the details that you entered about your travel should be like associated with that carbon offset, which is one of the ways that you can match that. So there's a bunch of different ways that you could establish verifiability, right, of like particular regen offsets. You could do it manually, like I just described. You can have an oracle between regen and whatever network you're trying to use to validate this. Or you could also just make a provenance node, right, that just manually has its own sort of integration with regen. And so all of those different methods are possible. But again, it's really based on what you're trying to do and what the requirements of your project are.
Okay. Thank you, Alan.
Thanks so much.
Again, it was Alan from Filecoin Green. Thank you, everybody, and I wish you a good day.